start?
Ready as I'm going to be.
Okay. So I will start recording now. Good morning, everybody, and welcome again for this another seminar here at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we have a very special visitor, Dr. Nick Schneider, from the Laboratory of Atmospheric and Space Physics in the University of Colorado in USA. And he will talk about surprises from Maven at Mars, Aurora, meteors, showers, and new water loss paradigm. Nick Schneider is a planetary scientist at the University of Colorado in Boulder, in United States. He leads the remote sensing team of NASA's Maven Mission to Mars. He received his PhD from the Lunar and Planetary Lab at the University of Arizona in 1988, where he also did a postdoc. In 1990, he joined the faculty in the Department of Astrophysical and Planetary Science at the University of Colorado and holds a research appointment at CU Laboratory for Atmospherics and Space Physics. He received NASA's Exceptional Scientific Achievements Medal for his Maven research and the Emmons Award from the Astronomical Society of the Pacific, a national award for undergraduate astronomy educations. With Jeff Bennett, Megan Donahue, and Mark Voigt, he co-authored the most widely used textbook in astronomy with cosmic perspective. So, Nick, thank you very much for this, for accepting this invitation, and the floor is yours.
Thank you very much. Can you hear me okay? Testing,
yes.
1, 2, 3.
Yeah, perfect.
Good. And so the first thing I want to do is to say muchas gracias por su hospitalidad, and especially to Francisco, with whom I've been working for many years, who also brought the sweets for everybody brave enough to attend. This is the first hybrid seminar in 2 years. Is that right? Wow. And also to Miguel, who's been a great collaborator with Trace Gas Orbiter mission. And I wanted to also express my gratitude to the students and postdocs in the program here that I've gotten to know a bit in recent weeks, and they have been happy to share their appreciation of Spain and Granada. And as a result, my wife and I feel like we are honorary Granadinos, if I'm saying it right. So as part of all this, we've had great times talking to everybody about the opportunities. Oh, sorry, I'm getting now the blinking yellow light. That's not so good. I apologize that my presenter tool now seems to blink the wrong color. Wow. So this actually worked just before the presentation. Does anybody have ooh, that's a special battery. That's a AAA battery. I need one. And part of our introduction to the culture here has been a list of movies and songs and expressions and things to learn about. And the grad student said that I should check out the Nokia ringtone, which is a Spanish composition. Francisco gave me a list, and Miguel gave me what you see on the left side here with links and lyrics, and I think he's going to give me an exam. But I look forward to that. But again, thanks also to the Severo Ochoa visitors program, very generous, very excellent support, and Manuel has been a major reason that has gone well. All right, so what I'm talking about today are a little bit about Mars and Maven, and then I'll get into some discoveries that we made along the way while we were doing our primary science mission. And since not everybody is a planetary scientist in this group, what I'm hoping to accomplish also is to show how the way that we do planetary science is to connect the different aspects of a planet, whether it's its interior with the magnetic field or the geology of the surface or its interaction with the sun. All these phenomena are closely related. I'm a teacher at University of Colorado, and so I'm fully accustomed to equipment failures, and with full expectation of recovery. And that was pretty good. Okay, so I've talked about the topics today, but I want to share that I have the benefit of representing this amazing group of scientists, everything senior scientists down to undergraduates, and I'm proud to say that everybody in this picture has been the first person on Earth to know something important and interesting about Mars. It's one of the reasons why we do missions through universities. So the background on Mars is stems largely from our understanding of comparative planetology, and what's the takeaway from this picture is that Mars is substantially smaller than the Earth. Small planets behave differently geologically and weaker gravitational fields. Mars, also being farther from the sun, is inherently cooler unless there is a substantial greenhouse effect. And so our vision of early Mars is that it was actually more Earth-like. It would have had a hot interior, ample volcanic activity, because we see Olympus Mons, huge volcanoes there. They filled the atmosphere with carbon dioxide, water vapor, other gases. And back then, Mars was warm enough inside that it generated a global magnetic field, which performed that the function of a protective bubble around the planet. And as you see in the diagram here, it prevented the solar wind from directly interacting with the Mars atmosphere. So thick atmosphere, maybe 100 times more atmosphere than is present on Mars nowadays. Just about all greenhouse gases, and that would have been enough to overcome the greater distance and make liquid water possible on the surface of Mars. We now know things are different. Mars is cold, nearly geologically dead, almost no atmosphere, and it's been a central mission of NASA to understand why it changed, because that's how Mars lost its conditions of habitability. Many hypotheses were proposed over the years, but the current hypothesis is that Mars' small size led to the cooling of the core, the loss of the magnetic field, and therefore the ability of the solar wind to pass directly by, and you might say through, the outer layers of the atmosphere and carry it away. So Mars, also being a smaller planet with weaker gravity, another escape mechanism is possible there. So the volcanoes have mostly ceased. They're not supplying the atmosphere anymore. So we call this the textbook theory. It's in the textbook. But until the Maven mission, this had not been tested. And in fact, there were many other hypotheses. But the geological evidence is remarkable. This is a now famous crater on Mars, Jezero crater, where the Perseverance rover has landed right somewhere around here. It's a crater 50 kilometers across that once was filled with water, and this channel would have supplied the rainfall that would have actually funneled the water into the crater here. No matter who you show this to that has a little geological familiarity, they look and say that's a river delta. It's exactly the geological interpretation of the Mars photogeologists. And as a planetary scientist, you look at this and say, but there are a lot of craters on it, more than you'd find on any river delta on Earth, which means this is billions of years old. And in fact, the atmosphere must have disappeared billions of years ago to leave the circumstance like this. One of the many beautiful parts of this picture is the color scheme, which is infrared signal measuring chemical composition of minerals. And what you see in the green color here is clay, technically phyllosilicates, identified from orbit. And so this would have been a mucky bog billions of years ago, and therefore an ideal candidate for where life might have been present back when Mars was more habitable. And of course, that's why Perseverance is now going around picking up rocks, putting them in a bucket, hoping those rocks will get a ride home in a few more years. So Mars was warm, wet, lots of greenhouse gases in the past, and the question then becomes, where are those volatile ingredients now? And one of the early hypotheses was that these ingredients, both dry ice and water, that were frozen out at the poles. They sent the missions, they did radar, they did chemical sounding, and there's not nearly enough of those frozen materials there. Water could be present in the form of permafrost. CO2 could be present in the form of limestone. That same camera that found clay found virtually no limestone exposed anywhere on the surface of Mars, and so not nearly enough. And so all these hypotheses that those ingredients were locked in the interior didn't work out, and the only alternative is, if it didn't go down, it went up. So the Maven mission is designed to test the hypothesis that the atmosphere could have escaped to space. And on our team, we have people who have studied those processes, including skeptics that think that it is not possible. The measurements have as you'll hear, turned out otherwise, but I'll tell that story in a bit. So we sent Maven to Mars to first understand the atmosphere as it is now, and secondly, look in detail at how the atmosphere is escaping to space, and then run the numbers to see if it's possible for the conditions of the early solar system, a very active sun back then, would have been capable of dragging away 99% of the atmosphere. Okay, so the spacecraft is about the size of a bus, I'd say a regular bus, not the ALSA double length buses. And you can see we have a lot of acronyms. It's the main payload. And most of these are charged particle instruments that either measure the particles or the fields, because those are major influences on atmospheric escape. And down here on the boom is the only remote sensing instrument to study Mars, the Imaging Ultraviolet Spectrograph, which will be the focus of my rest of my presentation. And we are, I think, the 5th ultraviolet instrument to go to Mars, and so we'd better do something new and different. One of the things is that we are mounted on a boom with 2 gimbals, and that means that when the spacecraft is charging up the batteries, looking at the sun or communicating with the Earth, that our instrument can be looking down and looking at Mars. So we are always observing somewhere. There's somebody in the room or on Zoom that loves diagrams like this. This is for you. And this is our instrument showing very sophisticated ways that we can bring light in through 2 different fields of view. We have a scan mirror so that we can map out the surface or even measure the atmosphere at different heights. And we have 2 different gratings that we can use, including one that allows us to spread the Lyman alpha signal from hydrogen and deuterium to separate them out and measure them independently. So the instrument is actually quite large compared to other instruments that have been sent before, because we knew that we had to do it right. And don't worry, these were removed before flight. Everything is good. So LASP builds amazing instruments, and NASA says you must do A, B, C, and D, and do them to the promised accuracy. And the lesson of space missions is that you build a great instrument that meets those requirements. You're going to discover E, F, and G, and we're up to X, Y, Z, which I get to tell you about today. So the strengths are that we can observe so much of the time, and following on all the past missions, we have designed a spectrograph that is really focused on important science questions. We have an orbit that is sometimes swooping close to the planet. We can study the atmosphere up close, even smell the atmosphere with a mass spectrometer on board. And at other times, we're far from the planet and can take images and measure solar conditions. And one of the things that I like is their ability, therefore, to do issues across planetary science. So here's to show you the very elliptical orbit and the way that we scan the atmosphere or image the surface. And I'll give you some more examples of this in a bit. The main way we take data is spatially resolved spectra. And there's somebody in the room or on the call that loves a spectrum, and this is for you. None of these spectral features that you see here are actually any different than what was seen more than 50 years ago by the first Mariner spacecraft. Nonetheless, we get incredibly high signal to noise, and we're able to map and monitor the brightness in ways that we've made substantial discoveries. The beauty of a spatially resolved spectrum like this, in this case of the atmosphere, is not only that you can identify what the ingredients are, but you can see which ones are confined to low altitudes, like these emissions from carbon monoxide, which is broken out of CO2, bound close to the surface. Oxygen, and especially hydrogen, just goes up and up. It goes off scale here. And this is an instant indication that atmospheric escape is occurring, especially in the atomic form. They're much lighter and able to reach higher altitudes. So what we normally see on the Mars day side are emissions from carbon monoxide, that's from the instantaneous breakdown of carbon dioxide. And this is from the instantaneous ionization of carbon dioxide here. These are very normal, repeatable signatures. On the night side, we sometimes see nightglow. It's a project I'm doing with Francisco. So I'm going to give you some information overload now, because it's actually quite remarkable the way we can take this data and ingest it and make sense out of it. I showed you the two directions that we can look, and we choose to put our scan mirror and a slit in one of them, and we can either zigzag here or here to look at the atmosphere or the surface. And everywhere we look, we take a spectrum about every 5 seconds. We had to go on a logarithmic scale here to see the hydrogen and oxygen, and we're kind of off in the at high altitudes here, so we're not seeing the other molecular species. But now we're going to ride on Maven for 20 minutes, and you'll see the slit moving back and forth, the spectrum changing, just a little bit faster than real time. And all those same spectral features that I showed you are being accumulated. We choose one, and we can actually build up this map of the atmosphere here. So we've got the compositional information, the altitude information, temperature information, and it's a great data set. And there's nothing like a data set collected consistently over and over again through seasonal changes, changes in solar activity, etc. So now we're going to look at what happens when we study the surface. Whoops. Well, that's what we get. No. Okay, let me see if I can do this better. And so this is going to be reflected sunlight that we're seeing from the surface of Mars. And again, we can choose a wavelength, that's the spectrum of reflected sunlight, and construct a two-dimensional image, even though we just have this tiny slit that we slide across. And I've chosen a wavelength that actually has an absorption in the middle of the ultraviolet from ozone. Well, we know that ozone is rare on Earth's poles. The chemistry of Mars causes ozone to be present on its poles. And in fact, this absorption here indicates the strong presence of ozone there. So we're able to make maps of Mars, images, and this processed image is data we were never supposed to take because the spacecraft people didn't tell us that they could get their download data rate as high as we needed for this. So we were ready. We modified our observations. So you can see the whole planet. This is Valles Marineris there. We can't see the bottom in the ultraviolet because of Rayleigh scattering, which is very strong at short wavelengths. That's the haziness that we see around here, Rayleigh scattering. Olympus Mons is right there, and it is taller than the atmosphere is. It sticks out through the atmosphere. There's still a little bit above it, and so there's a cloud on top of Olympus Mons and 3 other volcanoes that you have right there. Dust storm is happening there. There's the signature of ozone that I described previously. We can take these images every time we come back to that same distant point in the orbit, about every 5 hours. And this is what we saw over the course of a day, was the planet rotating. These are interpolated images to give you the progression of the appearance. And you can see that these clouds are building, building, building. And by the end of the day, they form this cloud bank, which is thousands of kilometers long. So there still is enough water vapor in the atmosphere to give rise to clouds just like this. And I bet you have something similar in the Sierra Nevada, especially in the summer, that in those over those mountains, you get the formation of clouds in the afternoon. So even though it makes sense from a planetary science sense, we got this headline from the Weather Channel that we had no explanation. So is there such a thing as bad press? Well, maybe. So those are the capabilities of the instrument. And now I'm going to talk about 3 different things, 3.5 different things that we discovered. The first of them was a good news, bad news story. If you've heard of the Comet Siding Spring, you know that it was discovered more than a decade ago and was predicted to have a very close passage by Mars, 140,000 kilometers, closer than any other comet passing by a terrestrial planet. And so we were actually able to image the comet in Lyman alpha light because the water that comes off is also broken down, and the hydrogen can be imaged. I should back up and tell you the story that when it was announced that there was going to be a comet encounter, the scientists went, "Hooray, a free comet mission." But the engineers went, "Oh no, cancel the mission." They actually proposed to wait 2 years until it was safe to go to Mars. So we had a discussion, and in the end, we went to Mars, but Maven and all the other Mars spacecraft timed their orbits so that they would be behind Mars at the time of maximum dust passage. And so Mars is taking care of its robots. That was good news. So the comet was coming. It was actually kind of fading a little bit, and we didn't know what to expect. We had a meeting ahead of time. 9 people had 10 ideas about what would happen at Mars as a result. And you're welcome to form your own ideas about what should happen. So this is the before spectrum. There's just the same features that I showed you before, just from the breakdown of carbon dioxide. And we're sort of, the data is coming down and we're leaning into the screen saying, what did you see? Anything at all? And boom, the brightest feature in the Mars atmospheric spectrum, I'm seeing some raised eyebrows, ours were raised as well, ionized magnesium. This is vaporized comet dust. This is the result of meteor shower, meteor storm. Well, what we did was to take all the numbers of the brightness, you know, we're astronomers, we know how to take brightnesses, convert them to densities. We knew the time over which the all that mass had been deposited. And the math is here, but what's interesting, it's 3 to 16 tons of cometary dust deposited in a matter of hours. And you take that mass and you put it in the size of cometary dust particles, and you get thousands to tens of thousands of meteors per hour. And this means many meteors in the sky at once, continuously for hours. The great thing about this bright signal that we discovered is we learned that emission line in great detail. That was not predicted. We didn't have a team member to study this. So we said, hey, you, Krismani, you're a grad student, go look at this spectrum. And he found magnesium every day of the mission because there's a steady supply, as you expect, just from the same kind of things that give us shooting stars. And the physics of this is important because this is the way high atmospheric clouds are seeded on Earth, mesospheric clouds, and so it's a source of nucleation now and almost certainly in the past on Mars, which could actually change the, contribute to climate change. But just to take this as sort of a human experience, you know, what if we had been there? The closest thing was actually the Leonid meteor shower of 1833. And this is not really scientific instrumentation here, but it gives this sense of the sky filled with meteors. And this was observed around the world. In fact, even the Native Americans that witnessed this event, it was the way they marked this year, the year of the meteors in 1833. So truly astonishing event. And one that has consequences for the climate of Mars because of the supply of cometary dust for nucleation. So it would have looked like this if you had ultraviolet eyes. For magnesium, there almost certainly was an equivalent one for sodium, which would have been the yellow color of streetlights, and that would have been visible at the time. Some people are surprised to learn about this metal layer in a planet's atmosphere, but we have one too, and we use it in astronomy because you can shine a laser from a ground-based observatory tuned to the sodium wavelengths. It makes an image at the sodium layer, and then you can use that as a reference for adaptive optics. Okay, so that was our first surprise, and it happened just right after we arrived at Mars. It was amazing that we were ready to observe and that everything actually worked. Another thing that we didn't expect there was aurora, and you can say, why don't you expect it? Well, on Earth, the aurora is usually found at the edge of Earth's magnetic field. has anybody ever seen the aurora? So it's because you have to like go to strange places to see it. It only rarely comes to where we are. So nobody really expected Mars to have a lot of auroral activity because it doesn't have the global magnetic field. Mars Express in 2005, however, discovered that there are sort of mini auroral features because even though there's no global field anymore, the field that existed billions of years ago was locked into lava flows, remnant magnetism, and that was enough to funnel the particles in to cause these little patches of emission that you see here. So Maven actually was able to take images of this phenomenon that we call discrete aurora because it's really finely detailed. This was an undergraduate. We said, "Hey, Cami, go look at all these pixels and tell me if it's an auroral spectrum." And she did, and it was, and it's great. And then we said, see where they land on the map of the crustal fields. And the red areas are where the tiny magnetic bubbles exclude particles. And these lanes in between are where the charged particles can actually go in and excite the atmosphere. And so it confirmed this theory about discrete aurora. So we've actually learned how to do this even better thanks to another undergraduate student that has found this on many, many more occasions. But it didn't stop here for aurora. So again, shortly after we arrived, we were looking at the night side and seeing the chemical reactions that makes the atmosphere glow. That's normal and expected, also seen by Mars Express. But then we saw something kind of weird. This is ultraviolet image of the entire globe in the night side. It was daylight over here doing its daylight thing. And all around the edge of the planet, you can see the atmosphere lighting up. And this is over a matter of hours in September of 2017. This was an incredible space weather event that was measured at Earth and at Mars. And not just by us at Mars, the Curiosity rover has a radiation sensor to say whether or not humans, if they're there, whether they should get underground. Because the radiation is hazardous to your health. And so at the same time that this was happening, the RAD instrument was saying, danger, danger, get underground. And so it's amazing that these phenomena are connected, that we're able to measure these hazardous conditions, even from orbit. So diffuse aurora is what we've named this one because it is global. There's no place on Mars which can exclude this. These are relativistic particles, and so it doesn't matter even what those small fields are, they're just going to be, the whole planet will be engulfed. And this, we sort of did a dope slap and said, what did you think was going to stop those particles from entering the Mars atmosphere? Anybody could have predicted this phenomenon, but nobody did. And it's just another measure that sometimes you have to go there in order to make these discoveries. And the other thing that's amazing about this, it gets really low in the atmosphere. This is about 50 kilometers lower than Earth's aurora would occur through similar physics on Mars. So this is down, it would be in our mesosphere here on Earth as well. And it's probably causing chemical reactions in that location. And this could even affect the chemistry of early Mars atmosphere when the sun was more energetic. So the aurora story continues with this spirit of discovery. We observed that hydrogen corona around Mars that I showed you in the spectrum early on, like this cloud of hydrogen, which is several Mars radii large. And normally it just makes this glow up above about 150 kilometers and not much below that. There's not so much hydrogen there. But sometimes we actually saw this layer brighten up. And this is not extra hydrogen, because remember, hydrogen very light, it should be very, very spread out. This was an indication of solar wind particles entering the atmosphere. They actually undergo charge exchange up here. So a solar wind proton becomes a fast neutral, and it can get through the induced magnetosphere and enter the atmosphere. So it's now a hydrogen atom, and it goes in and bangs into carbon dioxide. The electron gets excited and emits and gives us this signal. So this is a form of aurora where the precipitating particles are doing the radiation, not the background atmosphere in response to being bombarded. And this turned out to be also a very significant process, diagnostic not only of the solar wind, but also when the corona itself was very, very extended. And I'll talk about why that happens in a bit. So in image form, this brightening around the edge is what proton aurora looks like. And we discovered this really strange phenomenon that had happened in a particular season on Mars. And I should talk a little bit more about seasons on Mars. Mars has a tilt which is similar to Earth's tilt. And so it'll just go through opposite seasons in opposite hemispheres, with an interesting difference. The Mars orbit is sufficiently elliptical that Mars is much closer to the sun in southern summer. And so that's going to turn out to be the season of dust storms and a lot of other interesting activities that follow. So the seasons are very asymmetric on Mars. And what we've concluded from this is that the proton aurora is common when the solar wind is active and when the corona is enhanced, and the corona is enhanced when hydrogen is escaping. So this story about how did Mars lose its water also shows up in the aurora. So 3 different kinds of aurora on Mars is not what we expected. But it's all turned out to be very insightful about the interaction between Mars and the sun, thanks to the peculiarities of its magnetic field. And so a better way to think about aurora on planets is not that magnetic fields cause aurora, but that there are some kinds that exist because the magnetic fields are weak or absent. It's a broader definition of the aurora. And this is turning out to be important even in the study of exoplanets, because there's a hypothesis that you need a magnetic field to be habitable, and Mars is our nearby test case for this. And so there's a group of forward-looking exoplanetary astronomers saying, if we can see aurora, we know there's a magnetic field, it's likely to be habitable. Well, you have to be careful about what kind of aurora you're looking for, because they don't all have that link to a global magnetic field. So I think this is really making the same points here, that the magnetic geometry of a planet does control the kind of aurora, but probably all planets at some level have aurora. Okay, this slide I've shown to the exoplanet community, just saying be careful when you assume that aurora and global magnetic fields are linked. All right, so the next topic I want to talk about is the loss of water from Mars, and this idea that an ocean's worth of water has escaped to space has been is being tested thanks to the Maven mission. And I'm going to talk about 50 publications in 2 minutes that have studied every way that things can escape from the top of the Mars atmosphere. This is a simulation based on the charged particle measurements that show that thanks to the magnetic field sweeping past Mars, and its interaction with the ionized material just above the Mars atmosphere, there's a major streaming of charged particles. And so ion loss has been measured by the Maven mission. Our instrument has made the main measurements of neutral loss. Mars is down at this size. This is how far the hydrogen extends. And we can map the distribution of light from hydrogen, and the model results from that show that the escape of hydrogen and therefore the breakdown of water is also consistent with substantial escape. And so in 2018, we basically answered the question that Maven was sent there to study. Loss of gas to space has been the dominant process responsible for changing the climate of Mars from an early warm environment to the cold, dry one that we see nowadays. And so this combination of ion loss and neutral loss is enough to change the climate on Mars. So that's sort of by the numbers. We measured the rates, but the means by which it happened is a bit of a mystery. By the way, this shows our images of atomic carbon, atomic oxygen extending a little bit farther, and atomic hydrogen farthest of all. So I mentioned this idea that when Mars is closer to the sun, there's extra hydrogen in the corona. And that's not an obvious phenomenon. But the numbers, even from a proton measuring instrument, says that escape from Mars is much higher at this magic longitude around 270, where the planet is closest to the sun, as you see in the diagram on the right-hand side. But a member of our group, Mike Chaffin, undertook a really interesting study looking at cause and effect relationships about how you get the hydrogen up to the top of the atmosphere. And it's basically undergoing thermal escape. You know, the different Maxwellian distributions will put more or less material above the escape speed of the planet and put more or less material into the corona here. So how do you get H up to that boundary between the thick and thin parts of the atmosphere? So back when I was a graduate student, back in the second millennium, my advisor promoted the theory that that water can't reach high altitudes, but H2 made through photochemistry can, and this would be a slow process taking hundreds of years. And he suggested that the atmosphere would, that H escape would be slow and steady. But we observed that it's highly variable over the course of the year. So the new theory that Mike promoted is that in southern summer, when the dust storms are active, when the atmosphere is warmer, the middle atmosphere heats up. And what's called a cold trap, when it causes rain or snow or precipitation and the vapor can't rise any higher, that is broken and the vapor gets higher where it can be broken apart by sunlight and hydrogen can escape. We watched this happen together between Mars Reconnaissance Orbiter, Trace Gas Orbiter, and Maven in a dust storm, an isolated dust storm back in 2017. I'm going to march you through some really cool observations that showed how it happened. So there's an instrument, Mars Climate Sounder, that measured the abundance of dust. And here, it was 2019, and it shows that dust increased in early January. The next thing that happened is the lower atmosphere warmed up. The dust absorbs sunlight and it warms up the atmosphere. The next thing that happened was that the ice disappeared. The same instrument can measure ice. Up until this date, there's a lot of ice at that altitude. It goes away and then it reappears. Then we also saw this on our images. Remember those clouds over Olympus Mons and the Tharsis volcanoes? They're there, they're gone, and they're starting to come back. Where did that material go? It went to higher altitude. And so NOMAD, that Miguel and his team work with a lot, the instrument on Trace Gas Orbiter, and another spectrograph on Trace Gas Orbiter showed that the water vapor reached up to 70 kilometers, and that's high enough to start its breakdown. And on this same timeline, this increase in brightness right here is when there's more hydrogen in the corona. So all following this same, follow the water from the lowest altitudes out to space. And sort of the icing on the cake, in addition to this increased blue glow right here, bip, 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 this is proton aurora, telling us you have a very active corona at this time. So this story hangs together for the way that water loss from Mars is not slow and steady, but is seasonal. And it may have just been summer after summer after summer for billions of years that allowed Mars to lose that water. Okay, and so what I really like about this work is that it depended on having multiple spacecraft at Mars measuring the things that they do, the things that they each do best. And that's what allowed us to accomplish this. And I can't wait for the next Mars Southern Summer when we get to see what happens with the instruments now even better prepared to make these measurements. All right. I've just got another quick story to tell you here about the work that I'm doing with Francisco, studying nightglow. Nightglow is the bane of ground-based astronomers because it has this narrowband emission that shows up in all the astronomical images, and it can ruin data. But it's a beautiful phenomenon, and it's just caused by chemical reactions in the Mars, in a planet's atmosphere. And what we see on Mars is oxygen and nitrogen that have been split apart, that dissociation process, again, on the day side of Mars, they recombine, leaving a molecule in an excited state, and out comes ultraviolet photons in a very characteristic spectrum that I showed you early on. And you might say, well, the flow of material from the day side to the night side, huge atmospheric circulation patterns, I guess it's probably just going to show up all over the night side. Well, what we saw instead was this. I think this one is an animation. Is that at certain places and times, the atmosphere just brightens up and goes dim again. This is not a uniform process. What's especially curious is the brightest of these spots turns out to be 0 degrees latitude at the equator, 0 degrees longitude. And we had an undergraduate involved on this project at the time. And we went, Zach, when you had all the coordinates there, might you have set all the coordinates to 0? But no, he had done it correctly. And so we ruled out user error in that case. You know, you still might say, is it an alien base at 0, 0 trying to give us a signal? No, it was the physics of Mars' atmosphere is brightening up at that latitude and longitude. Here's a still frame assembled from our grand average. Here's how we mapped it. We turned to Francisco and said, please, could you spin up your Mars circulation model and turn on that chemistry that you developed and tell us what you expect for this set of seasons and conditions on Mars. And without fudging, without tuning, without anything, Francisco got us that, this bright spot at 0, 0. And we were just all blown away that this is what Mars does. It sent the nitrogen and oxygen preferentially down at certain latitudes and longitudes in the atmosphere. And as delighted as we were with this, it didn't match all the observations. And so I came here for this visit to say, Francisco, please could you make that happen about 20 kilometers lower in the atmosphere? And please could you just have it happen a little bit earlier? And so that's what we've been working on. We're going back and forth with reams and reams of computer output for these computer models. And it's been really great to see what has been accomplished thanks to his expertise with these models. Okay, so thanks. So these are the topics that I wanted to tell you about, and just these broad lessons that come in planetary science, especially with the interplay between different disciplines in planetary science. And to finish with what's ahead for Maven, I wanted to say that we're undergoing review by NASA for 3 more years of operation. Our mission team at Lockheed Martin is preparing for the demise of our gyros, because gyros rarely last 10 years, but they're going to set us up to work with star trackers instead. And we expect to operate, where do I say it? Maybe until 2030, because we're also the internet service provider to the rovers and landers. So we're going to keep doing excellent research with lots of collaborators, and I'm especially grateful for the collaborations. We've had wonderful discussions in the last couple of days about directions forward, working with Miguel's group, and Francisco just needs to find those right model conditions. But we're really delighted with the work that we get to do together. So thanks for your attention, and I'm happy to take questions about any aspect of the Maven mission or what went wrong on Mars. Thank you.
Thank you very much, Nick, for this wonderful wonderful talk, sorry. And now the talk is open for questions. So as we have 2 different kind of participants, please, if you have a question in the room, I think Francisco will manage, and then I will manage the one at Zoom. Raise your hand for the questions.
Okay, and did we decide that I should walk closer and,
Yeah.
and you should talk loud enough for this microphone to pick it up? Yeah.
So you asked a wonderful talk. I'm not a planetary scientist, so but I think I understood most of it. Thank you very much. It's enjoyable to go outside and have science fun, actually, and learn something new. Of course, my question is not exactly about Maven, but I was intrigued by the magnetic field that you presented at the beginning. So this hypothesis that you had a global dipole field, is this purely, I mean, you cannot really do paleomagnetism on Mars, can you? So this is really purely hypothesis at the moment, or is, for example, the samples that Perseverance is actually getting now, will you be able to do paleomagnetics with that in 10 years or in 50 years? Measures field strength, frozen in field strength?
It's a great question about Mars' ancient magnetic field. And Renee, could that be heard online?
Yes, it is, yeah.
So our information is very limited, but the magnetic field over those late lava flows that are dated to a particular age, the only way to get those is if there was a strong enough field. So people have taken those measurements from a spacecraft flying through those fields and say, if that's what's in the rocks now, and they cooled at this temperature like basalt does, the field must have been this strength. We don't know where the pole was. There was a hypothesis, since the field is observed to change, that it was indication of plate tectonics, which is paleomagnetism, but that theory hasn't really caught on.
Okay, we have a question here in Zoom. Cyril, please, go on.
Yes, thank you so much for the wonderful talk. I was wondering, you said that you didn't quite expect the ionized magnesium line after the comet shower. So were you just lucky enough to happen to have this line, happen to have a wavelength range which covered that line, or did you also start or planned with this magnesium line?
So no, that was very lucky. And we missed the sodium line, which would have been even brighter. So there was, magnesium was never in our plans, but it is a resonance line. And so it's a very strong emission feature. But no, we can't take credit for that.
I see. Thank you.
If there are other questions on Zoom? Okay. Wonderful presentation. I enjoy very much. I was intrigued by what you showed regarding it was the bright spot at the equator of the mall. Is it?
We quote your work, by the way. We quote your paper about.
But I was not able to finish to read the paper. Could you explain how can we explain the bright spot at the equator? Because I think it's by radiant circulation we are expected to see that more and cold, right?
It's a great question with a pretty long answer, but I'll.
Can you repeat the question, please?
Of course, the question was, how do you get a bright spot at 0, from a planet that supposedly has global circulation? Mars with strong seasons sometimes has atmospheric circulation rising over the summer pole and descending over the winter pole. But at other times of year around equinox, like is coming up here soon, the pattern changes and it mainly rises over the equator and descends over the poles, but it also descends on the night side. And so that would explain why the circulation is important over the equator. The spots, there are 3 of them at different longitudes, and that's a sign of atmospheric tides on Mars. These are, I like to think of these as a resonance in the atmosphere, that you've got the mountains scraping on the atmosphere from below and the sunlight heating it with a 24-hour period, and the whole atmosphere is vibrating. Your understanding of physics is a lot better than mine. And one of those happens at 0, and the oscillations of the atmosphere change the circulation patterns. And the real strength of his work, I didn't include this slide, is that that's the place where the waviness of the atmosphere causes the downwelling that brings those atoms from the high altitude to the lower altitude where they recombine.
It was possible to predict this with a model without any tuning.
Why had you not come it before in the model then? Because you never
I have to tell another story about Francisco. We presented this conference work at conferences, and there are many people with atmospheric models. And they would say, we see something like that. And I would say, why does it happen? And a lot of modelers will just say, that's what the model says. But Francisco was unique among them to say, let me ask the model. And so made the diagnostic plots to look at the velocities, to look at the influence of the atmospheric tides. I'll be honest and say that the modelers had a whole lot of years to play with the model when there were no observations to constrain them. And so we're coming out with a lot of observations that are going to change the models in the end. But it's this interplay of theory and observation, which is how we're going to make progress. And you need to have the right partners.
I have a follow-up question. Are we supposed to see the same pattern with the O2 Aurora? Yeah, nightglow, right?
Oh, there's another form of nightglow from oxygen, and I don't know the answer. That happens at a different altitude, and so I don't know.
No, it's always okay. Okay, so we are not supposed to see the same pattern.
Would be surprised if it's much different. Probably similar.
Okay, so I think you have just made a suggestion that he's that he's likely to look at. The oxygen nightglow is, those observations were made in the infrared, but not with an instrument that can map the planet in as such detail as we can. So I'm not sure that they'll be able to constrain that, but it's worth looking for. After you've solved our problems.
I have listened to you several times in the past, and it's always a pleasure to listen to you again. So I really thank you for this beautiful talk. I suppose all the students around are particularly delighted. And I have a question.
Is this about the songs that you gave me?
No.
That one about the onions was too sad. Okay.
But you mentioned one thing, which is, one of the first times that I heard about this seasonal variation in scale, I was so surprised. I couldn't believe it. But later, what is surprising to me is that why that was not, proposed before or thought about. And I don't know what is your opinion about that. But let me ask you the more important question for me now, which is, you mentioned there that now we know there are seasonal variations in the scale, but this seasonal variation is not related in principle with the amount of dust, or not necessarily. It is related to the amount of dust because in the season, this season is in the helium, there's a lot of dust, there's a lot of southern summer, etc. But during dust storms, it's especially then. There is also a lot of injection into the atmosphere, you know that very well. And what is your thought about, I think nobody knows the answer, but I'd like to know what do you think is more important, the seasonal variations or these peculiar huge injections, or what are they going to happen?
So I could give you an opinion, but you're right to point this out as an open question and to repeat clearly. Lots of things happen in southern summer. Just the whole atmosphere gets warmer. There are more dust storms, sometimes global dust storms. Which of those effects is most important? And we don't know. The one that I showed you was a regional dust storm. It was kind of small on a global sense, but it seemed to cause more escape than even the huge global dust storm. So it's a good thing that Maven and TGO will observe for more years, because we now have one season, one southern summer studied, and that's not enough to give an informed opinion.
We'll be looking at that, but I think it's Maven. We should give the final answer.
Maven will talk about whether or not the escape is large or small. But we need to know, was there a lot of water brought to intermediate altitudes? And that's where NOMAD and ACS on the trace gas orbiter come in. So I want to know the answer as much as you do. There's also a question of how far back in time is this the most important mechanism? Mars, when it was warm and wet, did not have dust storms. So how do you model that ancient climate?
One of the things that blew me away is you don't need magnetic fields for aurora, which makes all the sense in the world, but I've never thought of that as no one thinks of that. You just need an energetic particle that penetrates an atmosphere. So has anyone looked, for example, Titan has a strong atmosphere and probably no magnetic field whatsoever. So has anyone tried to find aurora or night auroral activity on Titan, for example? Or is it inside the magnetic field of Jupiter, Saturn, or I'm not sure.
So it's you got the proper takeaway message. If you think you've discovered a new phenomenon, you should test it in similar conditions elsewhere. So Titan does have excitation directly from the sun, but it's not, the quantity of data is not enough to really know if it's exactly the same phenomenon. What I find interesting is that moons embedded in planetary magnetospheres like Io and Europa, favorites of mine, they have this kind of global aurora as well. So it does happen. I think that Venus, actually, no, I should say, ground-based observers have looked at the night side of Venus, which is not an easy observation to make, and have seen oxygen emission correlated with solar activity. So Venus is, has this kind of diffuse aurora because it also has no global magnetic field. So each of the things that I showed you today were surprises that anybody could have predicted, but nobody did. And that is a real lesson of planetary science, that sometimes you just have to go there. And very personally for me, we went with an instrument with broad capabilities. And if we had designed something that only looked at hydrogen and not adjacent wavelengths, we might have answered that one question about hydrogen escape, but we would never have discovered these other phenomena. So sometimes you have to build a general purpose instrument, because discoveries 50 years after the first ultraviolet instrument are still happening.
Yeah, just thank you. Just a simple question. The new paradigm for H escape, does it rule out the ancient one, the more steady one with H2, or it's a mixture of both?
So it's a good question over, does the old theory for hydrogen escape through molecular hydrogen still happen? And the answer is it's negligible compared to the new mechanism. So this is what happens. This is also the difference between assuming steady state versus saying things can happen episodically. And in geology, it was what was it? Uniformitarianism. I forget the geology happens gradually versus things can happen very rapidly. That's a change which is still happening in planetary science. Consider the time variable case and not the steady state case.
More questions for Nick?
These have all been really great questions. And this is, Mars science has still got so many unanswered questions. And they're at a level where you've already proven that people who don't study Mars all the time are right in there with the insightful questions.
Okay, seeing none questions, either in situ or online, I want to thank again Dr. Nicholas Schneider for this wonderful talk. And please enjoy the rest of your stage here at IAA in Granada. Thank you very much.
And I'm so grateful to the Institute and my hosts and all the staff and students that have made it a great visit. I'll be sorry to leave and eager to come back. Hasta la próxima.